Good afternoon, class. We are looking at Chapter 5, Trigonometric Functions, Section 1, Angles and their measure. All right, so we are going to cover angles and their measure, trigonometric functions, unit circle approach, properties of the trigonometric function. The objectives are: convert between decimal and degrees, minutes, seconds, measures for angles, find the length of an arc of a circle, convert from degrees to radians and from radians to degrees, find the area of a sector of a circle, find the linear speed of an object traveling in circular motion. Reminding you of exponential functions, f of x is a to the power of x. A must be positive, a can't be 1. And it's a continuous function. So when a is larger than 1, looks like that. When a is between 0 and 1, that's an exponential decay. Can't be 1. If it's a 1, it is not an exponential function. What is it? It's a horizontal line. Okay, so it's not an exponential function, everybody. It's a horizontal line. So what do we notice? We notice we're talking about A and C. Horizontal asymptote is the x-axis, which has the equation y equal to 0. There is no vertical asymptote, VA short for vertical asymptote. The y-intercept takes place at 0, 1 in both cases. X-intercept, we don't have any x-intercept. Domain is all real numbers. In fact, even for this one. The range is from 0 to infinity. Remember, the horizontal asymptote is the x-axis. It never touches that. So what's the difference between these two? If a is larger than 1 here, it's an increasing function, which means limit of f of x as x approaches infinity is infinite. That means the first quadrant. X gets larger, so does y. But limit of f of x as x approaches negative infinity, it approaches the x-axis or equal to 0. On the other hand, if we are dealing with this one where a is between 0 and 1, now it's a decreasing function. Limit of f of x as x approaches infinity is 0. And that gives us the horizontal asymptote. However, limit of f of x as x approaches minus infinity is infinity. This is the second quadrant. And also, what you have here is some of exponential rules, reminding everybody of a to the power of 0 is 1. A to the power of m times a to the power of n is a to the power of m plus n is known as the product rule. A to the power of m over a to the power of n is a to the power of m minus n, known as the quotient rule. This is pretty straightforward. These three actually are negative exponential rules. A to the power minus n is 1 over a to the power of n. 1 over a to the power minus n is a to the power of n. A over b to the power minus n, flip it over to the power of n, which means you just move the piece up or down accordingly to make it with positive exponent. And this is the power rule. A to the power of m to the power of n is a to the power of multiply these two. The last one is very obvious aspect. So these are some rules for exponential functions, reminding you of those. What about logs? Reminding that log x base b equals y is the same as saying x equals b to the power of y. So log, if b is larger than 0, that means the base, and b is not equal to 1, y equals log x base b is equivalent to x equals b to the power of 1. So take a look at this arrow. This makes it easier. If you follow the arrow, log x base b equals y means b to the power of y equals x. So this is a general log. That means the base can be any number as long as it's positive and it's not equal to 1. And it gives rise to the following. I hope everybody remembers that. For example, log 1 base b is 0. Log b base b equals 1. Log base b of b to the power of x is x. B to the power of log x base b equals to x. And these are the product, the quotient, and the power. Log of xy is log x plus log y. All of them have the same base, namely b here. Log of x over y is log x minus log y. All of them have the same base, namely b. Now we have a common log. Remember, in the case of a common log, the base is 10. So when we write log with x and no base, that means the base is 10. We don't want to write the base 10, and that means 10 to the power of y equals x. And I hope you can see the transition from here to here. Log 1 is 0, log 10 becomes 1, log 10 to the power of x is x, so on and so forth. Natural log, the base is e. So when we write y equals ln x means log x base e, we don't write it in this format. And it means e to the power of y equals x. And it gives rise to the following properties. So this is a general case. And these two are specific cases, common log, natural log. For example, ln 1 is 0, ln e equals 1, and so on. Now, the relationship between logarithmic functions and exponential functions is such that they are inverse functions, so they are symmetric with respect to the line y equals x. So for example, y equals e to the power of x and y equals ln x are inverse functions. So this is the change of base formula. Log x base b is log x over log b, and choose any base, for example, a, or common log, base 10, or natural log, base e. Okay. And finally, for this page, if you look at the natural log, okay, ln x is negative when x is between 0 and 1. This means, everybody, we are looking at this portion, okay? This means this point. Ln x is 0 when x is 1. And then this last part is here. So let's use this part. Ln x is positive when x is larger than 1. So there's some stuff from prior knowledge of mathematics is important to know. We continue as far as the equations are concerned. Logs and exponential functions, you want to pay attention to the base, and you want to pay attention to the exponent and the arguments. So if you look at this one, for example, they have the same base, they must have the same exponent. In those two cases, they have the same exponent, they must have the same base. So if you look at this case, logs, if we have the same base, they must have the same argument. So if x equals y, the two logs are equal. And by the way, x and y must be positive. If you look at this case, they have the same argument. X is considered the argument. A and B, the base must be the same. X is positive, A is positive, B is positive. So these are some information, again, from exponential functions. We are still looking at prior knowledge of mathematics. Reminding you of a simple interest, I equals PRT. Compound interest, A equals P times 1 plus R over N to the power of NT, compounded N times per year. When interest is compounded continuously, the balance A in the account at any time T can be calculated by the exponential function. A equals P e to the power of RT. Sometimes they use P equals P sub 0 e to the power of KT. And I write both of them because it depends on the text. What is the future value of a lump sum of money? This is another way of writing it. P, where P0 e to the power of kt, or A equals P equals A equals P e to the power of RT. Doubling time for the population or investment to double in size, T equals ln 2 over K. The effective rate of interest is the equivalent annual simple rate of interest that would yield the same amount as compounding after 1 year. So when A equals P times 1 plus R over n to the power of nt, R of E is 1 plus R over n to the power of n minus 1. And in the case of A equals P e to the power of RT, R of E is e to the power of R minus 1. This is some stuff from before. I just wanted to mention that and the application, if you will, of some of these stuff that we learned. But now, actually, it's a good time to get started with our course. 5.1, angles and their measurements. Definitions for vertex, line, ray, initial side, terminal side, positive angle, which is CCW, counterclockwise. Negative is clockwise, standard position. We're going to discuss this as far as trigonometry is concerned. So this is a line that goes indefinitely on both sides. At some point, you have a vertex, and the ray is, in essence, you can think of it as a half line also, but let's see the definitions. Vertex. The vertex is the single point that is common endpoint of the two rays forming an angle. Line. A geometric object that is straight, has no thickness, and extends indefinitely in both directions. Ray. A ray is a part of a line that begins at a specific point, the end point, and continues forever in one direction. So, what is this? Here's the vertex. Here's the initial side. Here's the terminal side. And this is counterclockwise or positive angle. So, let's look at this concept now. Initial side. When forming an angle, the initial side is the ray that remains fixed in its starting position. Terminal side. The terminal side is the ray that rotates from the initial side to form an angle. The direction of rotation determines if the angle is positive, counterclockwise, this way, or negative clockwise. So here's the initial side, here's the terminal side, and this is going counterclockwise, positive angle, but this one is going the opposite side, clockwise, that's negative angle. Now you can go a complete revolution and continue again. This is counterclockwise and it is positive. Now, what about standard position? Initial side is always along the positive side of the x-axis. So theta is in standard position. And the reason theta is positive because we are going counterclockwise. Again, we have a standard position because the initial side is along the x-axis. The vertex is at the origin, okay? And so because this is going counterclockwise. Theta is in standard position, theta is negative. All right, we're going to continue. We're going to look at quadrants and quadrantal angles. Quadrants, everybody knows we have 1, 2, 3, 4 quadrants because we cut the grid in 4 parts. Here's the x-axis, here's the y-axis. This is the first quadrant, right? X and y are positive, or theta is between 0 and 90 degrees. Second one, theta is between 90 and 180. Third one, theta is between 180 and 270, and the last one between 270 and 360 degrees. On the x-axis, positive or negative. On the y-axis, positive or negative. Those are considered quadrantal angles. So we have quadrantal angles. Quadrantal angles have a terminal side that lies on the x-axis at 0 degrees or 180 degrees, or the y-axis at 90 degrees or 270 degrees. Those are quadrantal angles. So the terminal side is on the x or y-axis, positive or negative. So if we look at this one, you can consider 0 or 360 degrees. This one, 90 degrees. This one, 180 degrees. This one, 270 degrees. All of them are considered quadrantal angles. All right, we're going to continue with definitions. A right angle, straight angle. Let's see what we have. So as you can see here, and quadrants. This ends up in the second quadrant. Theta lies in the second quadrant. So that's very straightforward. The terminal side is on the second quadrant. This one, theta lies in the fourth quadrant, quadrant number 4, IV number 4. This one, theta is a quadrantal angle. So when we say quadrantal angle, it ends up to be on the x or y axis. It's on the negative side of the y axis, in fact, is 270 degrees. So if the initial side and the terminal side are the same ray, that means we've gone 360 degrees, one complete revolution, counterclockwise 360 degrees. The positive side of the y-axis, in essence, is the terminal side. A vertex, initial side, terminal side, right angle, that means 1/4 of a revolution counterclockwise, 90 degrees. So this is the initial side, this is the terminal side, this is the vertex. This is the vertex. So a straight angle, half of revolution counterclockwise or 180 degrees. And of course, this one is 270 degrees. Very straightforward, everybody. Example one, we wanted triangles and reminding everybody, here's the vertex, here's the initial side, okay? So if I want 45 degrees, here's the initial side, and I want to go obviously with positive 45 degrees. So I'm going to go this way and make a 45-degree angle. So that's the terminal side at 45-degree angle. If I want to go with negative, I'm going to go this way. And this one is positive, this one is negative 90 degrees. So we should have no problem drawing that. Now 225 degrees, that's positive. So you start from the ray along the positive side of the x-axis and you go 225 degrees. Bear in mind, this one is 180 degrees, so you have to go more and you end up in the third quadrant. Initial side, vertex, terminals. 405 degrees. So again, that's positive. You start from here, you go 360 degrees and 360 degrees. Then you have to go more by 45 degrees because this one, again, I want to make sure everybody can see this is 360 degrees plus 45 degrees, which means you're going to go a complete revolution and another 45 degrees. Okay. And what do we notice? These two are identical in essence. So here's another definition. Coterminal angles are angles that share the same terminal side. Look at the terminal side. When drawn in standard position with their initial side along the positive x-axis, they may differ by an integer multiple of 360 degrees or 2 pi radians. So as you can see, the difference between these two is 360 degrees or multiples of that, or multiples of 2 pi if you want to go that route. So this is coterminal with part A. Example 2, convert between decimal and degree, minute, second measures for angles. So what do we know? Number one, counterclockwise CCW revolution 360 degrees. 1 degree is 60 minutes. 1 minute is 60 seconds. So we use a prime here and double prime here. Convert 40 degrees, 12 minutes, 5 seconds to a decimal degree. Round the answer to 4 decimals. Let's see how we do that. So when we talk about minutes, 1 degree is 60 minutes. So 1 minute is 1 over 60. And 1 second is 1 over 60 times 1 over 60 or 1 over 3600. So we should know this. As a result of this definition, 1 minute is 1 over 60, 1 over 60 degrees, and 1 second is 1 over 3600 degrees. So we want to add those. So this is 40. This is 12 times 1 over 60. This is 5 times 1 over 3600. You put that into a calculator. And you get 40.2014 degrees. And they want 4 decimals, so that's fine. Now, the reverse process. Convert 78.562 degrees to the degrees, minutes, seconds form. Round the answer to nearest second. So this is the sum of 78 and 0.562 degrees. So 78 degrees is fine. This one, if we multiply it by 60, this part becomes in minutes. So the product of these two will give us this number. So that means this is 78 degrees and 33.72 minutes. So we keep this and we keep this. Now this 0.72 minutes We multiply times 60 becomes seconds. So we get 78 degrees, 33 minutes, 43.2, and we are going to the nearest second, so we don't, I mean, we round it to 43, and we write 78 degrees, 33 seconds, 78 degrees, 33 minutes, 43 seconds as the final answer, everybody.